Proportion testing. Problem 5 and problem 6. Proportion z-test for true population proportion rho. I'm always excited when I begin to talk about proportion intervals or proportion testing because we're back to z. And I think it's easier to work with z in many ways than it is to work with t. So whenever you have a proportion test, it is also a z-test, so z-table. The only difference is now, when you go here, you need to imagine with all three setups, two-tailed, right-tailed, left-tailed, that instead of mu, you put rho or p there for proportion. So you can have a two-tailed proportion test, a right-tailed proportion test, a left-tailed proportion test, but make sure your parameter is p or rho for all 6 of these. And you can still keep this for your test as long as you change out the parameter, the correct parameter. The test statistic formula this time is different. It is z equals, though, because it's a z-test, 2 decimal places, p hat sample proportion minus p or rho, that is your hypothesized proportion, divided by the square root of p times q divided by n. Now, this p or rho is different with confidence intervals. When we were trying to find E, the margin of error, we had the critical value, z sub c, times the square root of p hat q hat over n. This is not p hat and q hat divided by n for this test statistic. This is your claim portion, and this is q, which is 1 minus your hypothesized claim number. Again, p plus q must equal 1. This rho or p is the same as your p here, the hypothesized proportion, the claim number or claim proportion. With that being said, I think these are pretty general and basic. We're going to take the same approach with these 2 problems. Again, one of the 3 will not be represented. We can do a left-tailed, a two-tailed, a right-tailed proportion z-test for true population proportion, but I only have 2 examples in the packet. A recent survey found that 68.6% of the population own their homes. In a random sample of 150 heads of household, 92 responded they owned their homes. At alpha equals 1%, level of significance. Okay. Does that suggest a difference from the national proportion? Again, I feel like, and if I were to give you this same problem on a test, I just cut it out from a textbook and pasted it, to be honest, to this handout. The national proportion of 68.6%, I think they should have done that, to refer back to that first percentage there of 68.6. So first sentence, a recent survey found that 68.6% of the population own their own homes. That is going to imply equal to. You could also say 0.686. In a random sample of 150 heads of household, 92 responded that they own their own homes. At alpha equals 0.01, level of significance, does that suggest a difference from the national proportion of 68.6%? So the last sentence, and the last sentence is a question to us. So rho no longer equals 0.686. And we have to say, well, the sentences are opposite each other. One's the null, one is the alternative, and one is the claim. This has to be the claim because they are asking us this question, does this suggest a difference? It does not say, does this suggest that the statement holds true that it is 68.6%. It says, does suggests now a difference, no longer equal to 68.6%. So the claim rho does not equal 0.686. When you do your setup, make sure you put rho. If you have to, go to your sheet. You're looking for your claim symbol of not equal to, and it's an alternative statement. So the null has to be equal to. The claim's the alternative. So the first sentence is the null statement, and the alternative, the last sentence or the question to us, is the alternative statement, opposite each other. This is a two-tailed proportion z-test. For rho or P. And I'll just draw an arrow here. Critical values. Now remember, we're going all the way back to Z now. We draw a Z-axis, bell-shaped curve, shade both tails, and we're looking for a positive Z and a negative Z. And alpha was given to be 0.01, so each tail is alpha over 2. 0.005 is in each tail. Alpha divided by 2. I better box that. So when you divide that by 2, each tail is 0.005. I would just do, now you get good news, you can go back to using invert norm again because it's the Z table. So I would use invert norm on that bottom 0.005, and I believe it's a negative 2.58. So those are your two critical values, plus and minus 2.58. Yeah, we did this in another video or another problem. Negative 2.575, negative 2.58. So those are my CVs, my critical values that mark my rejection regions. Next is going to be the test statistic. Z equals P hat minus P divided by the square root of P cubed divided by N. Now we did not figure out P hat from up at the top, but P hat is 92 out of 150. If it's not a nice P hat, the textbook says to round to 3 places accurately. I get 0.613 repeating. So rounded is 0.613. That's what we're going to use for our P hat. 0.613 minus 0.686, the claim, divided by the square root of 0.686, and Q is going to be 1 minus 0.686. .314 is Q. And I did not draw my radical down here long enough because I've got to make sure I include divided by N, and N was 150. Again, since it's a Z-score, we round to 2 places accurately. So here we go. 0.613 minus 0.686 equals, there's my numerator, divided by square root, parentheses, 0.686 times 0.314, P times Q, divided by 150, and arrow out from underneath the radical, equals negative 1.93 if you round to 2 places accurately. So my test statistic here is a negative 1.93 also. The calculator may give you a slightly different test statistic because they're going to use the exact p-hat of 0.613 repeating forever and ever and ever. So do not be surprised once you round. The TI-8384 capability gives you something a little bit different. I think it gives you negative 1.92, but we'll see in just a moment. Decision. Put your test statistic in the picture, which is a negative 1.93 on the axis. So do not reject the null. It falls in the non-rejection region. Again, the null statement, what we do not reject, is the fact that rho is equal to 0.686. Do not reject the null statement. Now the claim is the alternative, but we're not rejecting the null. That means there is enough evidence to support the claim. Excuse me. There is not enough evidence to support the claim that rho differs from 68.6%. We cannot reject the null statement that says equal to, so we cannot support the claim that says differs. Or go here to play it safe. The claim is the alternative. Do not reject the null. There is not enough evidence to support the claim. Step 1, identification. Step 4, decision. Step 5, conclusion. And you're done with that particular problem. Traditional method, two-tailed proportion z-test. Now the p-value method, we take our picture z and we are going to put our negative 1.93 on the axis. That's our test statistic. We're going to find that area, and since it's a two-tailed proportion z-test, we double that area because it's, first of all, two-tailed and it's a z-test. So we double it by hand. So you would go to your z-table and look up negative 1.93, and it would give you the area below it because that's how the two-page z-table works. You could also use normal CDF. Negative 1.93. .0268. 0.0268. Okay. But we do have to double it. So the p-value final answer is 2 times 0.0268. And that is 0.0536. There's your p-value by hand using the two-page z-table. 0.0536. Please double. If this happened to be a left-tailed proportion z-test for true population proportion, and this was your test statistic for that left-tailed proportion test, then yes, 0.0268 would be your p-value. But since it's two-tailed, we got to find this and double it. Now, decision time. Alpha is given to be 0.01, and the p-value we just found is 0.0536. So you have two choices to put in the box, either less than or greater than or equal to. If alpha is less than, do not reject the null. If alpha is greater than or equal to, reject the null. So even though it's proportion testing, you still go here to make your decision. Greater than or equal to, less than, tells you your decision. Alpha is less than. So once again, do not reject the null. There is not enough evidence to support the claim. Sadly. I say it's sad because I always think of myself as the one that's conducting the test. And when you can support my claim, I'm happy. And when there's not enough evidence to support my claim, I'm sad. So, and it has nothing to do with this test. I'm also happy if I'm the one doing the testing and there's not enough evidence to reject my claim. That's in the case where my claim is the null and you cannot reject the null. I'm also happy if I'm the one doing the claiming and the testing that there's not enough evidence to reject my claim. Versus I'm sad if my claim is the null statement and the null statement is rejected, there is enough evidence to reject what I'm testing. Reject the claim. I'm sad here. So I like my claim, just me personally, there is not enough evidence to reject it, or there is enough evidence to support it. These are the two good ones for me, and these are the sad ones for me. There's not enough evidence to support my claim, what I'm testing. There is enough evidence to reject my claim, what I'm testing. So sad faces here, happy faces here. A report by the NCAA states that 57.6% of football injuries occurred during practices. That looks like to me the first sentence is stating equality. That row is 57.6%. Now the last sentence, a head trainer claims that this is too high for his conference. This trainer is against this statement. It's just too high for his conference to say that it is 57.6%. So he randomly selects 36 injuries and finds that 17 occurred during practices. Is his claim correct? So here's your question. His claim is referring back to the trainer who claims that this is too high. This number is too high for his conference. So if that number is too high for his conference, we have to think about what that symbol means. So I'm going to put row and 57.6%. And we have all kinds of symbols that we could put there, but it has to mean too high for his conference. So the report says that it is exactly 57.6, but a head trainer claims, no, that number is too high for my conference. So I'm going to test this claim that it's too high for my conference by selecting a sample of 36 injuries and finding 17 occurred during practices. And the trainer sets the alpha to be 5%. Is his claim correct? What claim? That it's too high. So if you think about the different symbols that could go here, because obviously this is going to be your claim. The first sentence is not your claim. This last sentence is your claim, what you're testing. That number is too high. So if he's saying that number is too high, that must mean for his particular institution, the trainer, if that number is too high, then that number, row, must be below 57.6%, less than. If he's saying it's too high, then he's claiming that it's less than for his conference. So, and that can be kind of complicated, but it just has to make sense. Less than. So the claim is less than 0.576. If you go to your setups, it looks like we've got ourselves a left-tailed proportion z-test. Less than is in the alternative, greater than or equal to is in the null. So we're going to have row less than 0.576 and row greater than or equal to. So here's your claim. The alternative by the trainer. Now the first sentence is still the null statement because it does say greater than or equal to, and it's opposite the claim statement, that it's too high for his conference. So for him, row must be below 0.576. So this is the claim. The opposite of less than is greater than or equal to if you look at your possible statements. And we know that too high must mean less than. Therefore, the null is greater than or equal to. So I'm going to name it. It's a left-tailed proportion z-test. To test his claim, the head trainer considers 36 injuries and he finds that 17 occurred during practice. So P hat is going to be 17 out of 36. Again, if it's not nice, then we will round to 3 places accurately. That's going to be 0.472 repeating. So we're going to do 0.472 to 3 places accurately. And it just dawned on me that I did not show the TI-8384 calculator for the first two-tailed proportion z-test. I will definitely show that to you for this particular test before I end this video on proportion testing. I apologize for that. It's not very difficult to put into the calculator at all. So this is left tail. So when we draw our picture, we shade the left tail, and that's all of the alpha they give us. We don't do anything to it. We do not divide by 2. That alpha determines our critical value. And I hope you know, if you look up 5%, that tricky 5%, your critical value is a negative 1.65. If you do invert norm on 0.05, you're going to get a negative 1.64 by calculator. But by hand, by using the z-table, a negative 1.65 is your critical value. Okay? Test statistic. P hat minus P, square root of PQ over N. So we used a rounded P hat of 0.472 minus P, which is 0.576. Under the radical, if P is 0.576, then Q has to be 1 minus. And I get 0.424. 0.424. Plugging this into the calculator, you would have 0.472 minus 0.576 equal, divided by the square root, parentheses 0.576 times 0.424, divided by 36 and arrow out from underneath the radical. Enter. Negative 1.26 is your test statistic. So I'm going to put that in my work here. A negative 1.26. Now when I put the test statistic in the picture, negative 1.26, it falls here on the axis. So do not reject the null. And the null statement is rho is greater than or equal to 0.576. Do not reject the null statement. And I'm kind of sad then for the trainer, because you know what that means. If we do not reject the null, what does that mean about his claim? That it's too high for his conference. If we cannot reject the null, then there is not enough evidence to support the head trainer's claim. That it's too high for his conference, but please indulge me and let me do this. There's not enough evidence to support the head trainer's claim that it's too high for his conference or it's less than 0.576. Now, p-value method. I am going to draw my z-axis, and I am going to put my test statistic of negative 1.26 here. Shade that. Good news is, because it's a left tail proportion z-test, that area is your p-value. You do not double it. So go to your z-table and look up negative 1.26. And it is here. And I get 0.1038, negative 1.2, 0.1038. Do not double. So the p-value by hand is 0.1038. And we're going to use that to make our decision. Alpha was 5%, and the p-value we just found by hand by table is 0.1038. Alpha is, compared to that p-value, less than. Do not reject the null. There's not enough evidence to support the head trainer's claim. Calculator time. You will go to Stat, and you will arrow over to Test, and it is number 5. It says 1 prop z-test. Enter. P sub 0 is the hypothesized proportion of 57.6%, but you have to put it in as a decimal, 0.576. He takes 36 injuries and 17 occurred during practice. And this was a left tail because the alternative statement, less than. So I want to arrow to the middle and press enter to say it's a left tail proportion z-test, and then calculate. You can see that the test statistic is negative 1.26 once you round to 2 places. The p-value is 0.1038. Oh, it agrees with what we have by hand. So that's wonderful. So we get the same p-value, and once we round, the same test statistic, negative 1.26. So great news. Well, not for the trainer, but we've concluded the problem, and we cannot reject the null, so we cannot support the head trainer's claim. And that is proportion. So I did a 2-tailed proportion z-test, and this is a left-tailed. I have not represented a right-tailed proportion z-test, and you, as the student, will wish to see or practice a right-tailed proportion z-test, both methods, since it's not represented in the video or in the handout. Thank you once again for being patient and